un doctorado en estadística por la Universidad de Harvard. Durante 2 décadas colaboró en el Departamento de Estadística de la Universidad Estatal de Pensilvania y ahora es el matemático estadístico senior del modelado analítico en la Oficina del Censo de Estados Unidos. Ha sido autor de 3 libros y docenas de artículos sobre estadística, bioestadística, metodología de encuestas, psicología cuantitativa, investigación de prevención y otros campos. Sus intereses de investigación incluyen datos faltantes, estadísticas computacionales, desarrollo de software, análisis bayesiano, muy bien, datos longitudinales, modelado de variables latentes e inferencia causal. Actualmente es miembro del Comité Federal de Metodología Estadística. Luis.
Good afternoon. Thank you so much for inviting me here. This is a real treat to be here. I realize that the time right after lunch is siesta time, so I'll try not to go too long. We're starting a little bit late, 10 minutes late, and I'm hoping that my talk will not go too long. It'll probably be shorter so we can recover our time. So today, I'm going to speak about an overview of multiple imputation for missing items in complex surveys. And I want to stress the word overview because I'm not going to get into details. My talk presumes that you know a little bit about what multiple imputation is. I'm not going to talk too much about what multiple imputation is. More introductory material will be given by Jörg tomorrow morning. But my goal today is to speak especially to people working on surveys and censuses and administrative databases to talk about how multiple imputation applies in your context. Multiple imputation was developed in universities in a very academic environment. And as we know, moving from theory to practice is very difficult. And so I'm going to talk about the practice in the complex survey world and just giving an overview, giving you entry points into the literature. My talk makes reference to over 50 articles. So you'll see a lot of references in my talk. The actual bibliography is in another file, and I put it on that computer, and if anyone is interested, I can send you the bibliography so that if you want to do more reading, you can. So this is an outline of my talk. I'm going to give some historical development on multiple imputation. I'm going to talk about how to do it, but how to is in quotes because I'm not going to go into details. I'm just going to talk about the big picture. And then the largest part of my talk is going to be dealing with the complexities of applying multiple imputation in complex surveys and censuses. And there are many, many problems that still need to be solved. And I'll finish up with some non-statistical considerations. So the historical development. The theory of multiple imputation has quite a long history. As far as I know, multiple imputation was first proposed by Donald Rubin way back in 1977 when he was working on a problem of missing values for income in the current population survey. So the income question has historically had a high non-response rate, and he was investigating ways to work with the observed data to get valid inferences for the population, and he suggested multiple imputation at that time. The full development of the rationale and theory for multiple imputation was published in Donald Rubin's book in 1987. His book is heavily cited, but still not too many people read it because it's very difficult to read. So it's the most cited and least read publication in this field. But still, you should cite it. About 15 years later, after that book was published, there were some criticisms of multiple imputation, mostly from a design-based perspective, starting with Robert Fay, who worked at the Census Bureau. In fact, I am now sitting in Robert Fay's former office. So, and Bob Fay is a very, very smart individual, and he began to criticize multiple imputation, pointing out some problems that arise when the model that you impute under is different from the model that you then analyze the data under. And in response to that criticism, Xiaoli Meng wrote a very, very nice paper in 1994 where he introduced the idea of congeniality between the imputation model and the analysis method. And that was a very important development. It began to treat in a rigorous way how you can get the right answer if you're imputing under one model and then analyzing under different assumptions. There was another round of constructive criticism of multiple imputation that started by Jamie Robbins in 1998. And the criticism there was of Rubin's variance estimate. After you do multiple imputation, you get an estimate of your quantity, and then you get an interval around it. And there's a variance estimate associated with that interval. And he criticized the fact that under certain conditions, that variance estimate is inconsistent. And Donald Rubin responded with some arguments in 2003, talking about why we don't really care about the variance estimate. What we really care about is the interval coverage. And he never intended to get a proper variance estimate. Now, as far as the implementation goes, so I just talked about the theory. To actually implement multiple imputation there's been a lot of development in that area. If you go back to Donald Rubin's 1987 book, he only talked about some very, very simple imputation problems. Univariate missingness, the problem of imputing a single variable, either continuous or binary, that's missing under linear and logistic regression models. He talked a little bit about a monotone missing data pattern, and I'm sure that Jorg will cover this tomorrow, but a monotone missing data pattern occurs when you can order the variables in your data set so that if one variable is missing, all the variables to the right are missing. So in other words, you order the variables in your data set so that it looks like a staircase where everything below the staircase is missing and everything above the staircase is observed. If you have that special pattern, then doing multiple imputation sequentially becomes very easy. And that was a subject of Donald Rubin's book. The more general problem of the multivariate missing data pattern, what we sometimes call that Swiss cheese, where you have a data matrix and you have holes all sprinkled throughout like Swiss cheese, that was computationally much more difficult. And in my book, which came out 10 years later after Don's book, I published some algorithms for doing multiple imputation in that multivariate Swiss cheese setting, with models for normal and categorical and mixed data using Markov chain Monte Carlo. And if you look in my book, it's very old, there's no mention of Markov chain Monte Carlo because that name wasn't developed then. We called it by different things. But MCMC is now the accepted term, and so that's what I'm using. Later, or actually roughly the same time, several groups around the world began to work on the notion of fully conditional imputation or sequential regression or chained equations. And that's a paradigm where you have a multivariate Swiss cheese pattern, but instead of imposing a joint model on all your variables, you only model each variable given the others. And so you have a sequence of regression models. Each one is a regression model for one variable given the others. And there are several software packages that can do that. One of probably the two most used are IVEware, which was co-written by Raghu, and Mice, which was written in R by Stefan Buren and his colleagues. And there are also many other specialized methods for doing multivariate imputation under an assumption of missing at random. And there are a few under assumptions of missing not at random under special models. But these are highly specialized, and they're not really useful for general problems. This is some information that I'm putting in just for people who are interested. This is a bit of trivia. The first general software for multiple imputation in a multivariate missing data problem, most people don't know this, but that first program was written by me while I was a graduate student at Harvard University, and it was a program written in DOS Fortran. I still like DOS. By the way, I wish I could go back to it. Whenever I log onto my computer, the first thing I do is open a DOS window. But as a graduate student, I met a historian of science named Frank Sulloway, who was working at MIT. And Frank Sulloway later won a MacArthur Fellowship, a MacArthur Genius Award, for his work on birth order. And his research was very, very interesting. He was interested in revolutionary ideas in the history of science, and he collected information on 25 or 30 revolutions in science over the last several hundred years. Some of the big revolutions that he collected a lot of data on were, say, Darwinian evolution, but there were many other minor revolutions in science, and he constructed a database where he tried to collect information on the scientists from the time, whether they supported the new idea or opposed the new idea. So he was trying to predict support for a scientific revolution. And he was trying to predict that from characteristics of the scientist, measures of religiosity, measures of social class. And in his research, he found that one of the strongest predictors of whether you supported an new idea in science or opposed was birth order in your family. Are you the firstborn in your family, or are you later born? And he found that laterborns were much more likely to support a new idea than firstborns. Now, you can imagine that if you collect this kind of historical data, there's lots of missing values in the data set. And so he didn't know how to handle these missing values in his data set. And I don't remember how I got involved in his project, but he ended up hiring me to write this DOS program to create multiple imputations. I had just figured out how to do it in a multivariate normal model. And he wrote this book. It became a top 20 bestseller on Amazon.com, but that's not saying much because Amazon.com was really small at that time. But he actually mentions me in the appendix, and he mentions multiple imputation in the appendix. So if you can see down in that second paragraph, he says, Joseph Schafer, a statistician who completed his doctoral dissertation on this problem under Donald Rubin, implemented an idea into a workable computer program. And that computer program I later rewrote several times, and it became rather popular, and I published the algorithm in my book. So that's a bit of interesting trivia, but and that was a very fun research project to work on. In terms of publications, Stef van Buren at University of Utrecht in the Netherlands has a very nice website on multiple imputation. And at his website, he has this graph where he shows the number of publications on multiple imputation, and he has a line for multiple imputations in the abstract and multiple imputation in the title. And this graph is the vertical axis is on the log scale, so you see a linear growth on the log scale, so this is exponential growth. And he says that about 2005, there was a turning point, about 10 years ago, where multiple imputation became widely accepted. Before that, if you wrote a paper on multiple imputation, you had to spend a lot of time arguing about not just what it is, but why you want to do it in order to get the referees to accept your paper. Now, it's to the point where if you don't do multiple imputation, the referees complain. So, and also every major statistical package does multiple imputation in some fashion. Now, for the rest of today, my time today, I'm going to talk mostly about applications to surveys, censuses, and administrative databases. And my experience is in the United States, so I'm sorry, these are mostly or exclusively examples of how it's been used in the United States. But there are, from what I'm hearing more and more, there are similar applications or even more elaborate applications in other countries. One of the earliest was a problem involving census, industry, and occupation codes. So every 10 years, the United States conducts a census, and at that time, we had a long form, a special long form for the census, where we asked many detailed questions, including, what is your occupation? And from one 10-year period to the next, the system for coding occupations changed. And so multiple imputation was used to create a bridge sample, as a sample where, an artificial sample where individuals were coded both under the old scheme and under the new scheme. And that helped data analysts to bridge the two systems. Now, there was an early application in the fatality analysis reporting system, which is reporting traffic deaths due to traffic accidents, and that's an administrative database. The consumer expenditure survey, Raghu and his colleagues worked on a technique for multiple imputation. It was for missing income, correct? Yeah, so that's the final, 20 years later, the actual implementation of Don Rubin's first idea. The National Health and Nutrition Examination Survey was a big multivariate imputation problem that I worked on in the 1990s. The Survey of Consumer Finances, which was the first application that I know of sequential regression. The National Health Interview Survey now uses multiple imputation, and there's at least one administrative database. This is I believe it's a California database, the Cancer Care Outcomes Research and Surveillance Network. I'm not sure about that one, I don't remember. But there's an increasing number of examples where multiple imputation has been successfully used in surveys, censuses, and administrative record databases. Now I'm going to talk very generally, and I mean very generally, about how you would do multiple imputation. And I'm going to present it in its most general setting, and Jörg will speak about more detailed, simple examples tomorrow. But there are basically 3 steps. And the first step is to generate the imputations. And so I'm going to use a notation similar to his. We have a set of complete data, which you break up into an observed part and a missing part. And then you have some response indicators. He used M, 1 if it's missing, 0 if it's observed. So I prefer to use R, which is 1 if it's observed, 0 if it's missing. But basically, these are variables that tell you which parts of Y are observed, which parts are missing. If you assume that the missing data are missing at random, then you can generate imputations as draws from a conditional distribution for the missing data given the observed data. And that conditional that model has some parameters, which I call theta, which are parameters of a data model. And so the message here is that if you want to do multiple imputation in the right way, you need to have a model for your data. This is a model-based technique. So we are not talking about the kinds of imputation techniques where you specify an algorithm and it's driven by the algorithm. This is driven by a model. And once you write down the model, at least in theory, you know how to create the imputations. If you don't assume missing at random, but if you have some model for the missingness that's not MAR, then you need a joint model for the complete data and the response indicators, and that will depend on some other parameters, which I call phi. And you have to, in each case, whether you're working with theta or phi, you have to include in your multiple imputations some assessment of the uncertainty in those parameters. And so this is an inherently Bayesian method. So we use Bayesian techniques to generate the multiple imputations. And that's why we use Markov chain Monte Carlo and things like that. So that's all I'm going to say about how to generate the imputations. I presented it in the most general light. Now the second step, which is easier, is analyzing the completed data sets. So after you generate multiple imputations, you have M copies of Y-miss, M simulated versions of Y-miss. And in the simplest case, what you would do is you would take your M versions of your complete data, analyze each one, and from each one you would save a point estimate and a standard error. So in this simple case, you have a quantity in the population that you want to estimate, call it Q. Could be a total, it could be a regression coefficient, a mean, proportion, could be just about anything, but it's a scalar quantity. And from each of your imputed data sets, you get a Q hat, pretending that it had no missing data, but the Q hats vary, and the variability in the Q hats gives you some understanding of how much uncertainty there is due to missing data. And then you also you also save the standard errors, one from each data set. Now, immediately a question arises, how does that estimand Q relate, if at all, to the parameters of the imputation model? In surveys, Q might be a total, a mean, a ratio, which is well defined apart from any model. Now, that led to some hard thinking about how the imputation model must relate to this question about Q in the population if you're going to get a right answer. And the method of multiple imputation does give you a correct answer if the imputation method is proper in a technical sense defined by Donald Rubin. And there's a very nice discussion of this in Steph Van Buren's book from 5 years ago. I'm not going to say much more about that because checking whether or not it's proper is a very difficult exercise and not many people do it. It's more of a theoretical concept. There is also a very nice discussion of this in Meng's 1994 article on congeniality, but that article is very hard to read. I was one of the discussants on that article, and I didn't understand it. And I wrote some things in my discussion that are wrong, but then I looked at all of the other discussants, and none of them understood it either, so I'm happy. Now, this theory about what makes an imputation method proper is not widely understood by practitioners. It's not widely understood by many of us who actually work in the field. But there are intuitive arguments that convey the main points, and I will try to explain those a little bit later. Now, the third step in multiple imputation is to consolidate the results. So you have M different data analyses, or it's the same analysis repeated M times. You take the results from them, and you have to combine them to get one answer. And there are many different ways to do this, but the best known and still most widely used technique is Rubin's rule for scalar estimands, where you compute a total variance, which is basically the sum of a within imputation variance and a between imputation variance. So the within imputation variance is the average of the squared standard errors, the average of the U squareds. The between imputation variance is the variance of the Q hats. And you just basically add them with a little correction factor. And it's analogous to one-way analysis of variance. But it is important to point out that that's not the only method, and there are at least 10 other methods for consolidating the results. There's a method where that works for smaller samples, and that's rules by Barnard and Rubin in 1999. There's an extension of this basic technique to a vector queue. There's likelihood ratio test statistics, how to combine those, and that's a nice technique, but it only works if the parameter space for Q is convex, so it doesn't always work. There's a technique for p-values, which doesn't actually work all that well. I don't recommend it. And there are some different rules if you're using multiple imputation for partially or fully synthetic data. So there have been proposals to use multiple imputation not just to replace the missing values, y-obs, but also, or y-miss, but to also replace the y-obs with synthetic data so that you can release it to the public and avoid disclosing sensitive information. If you do that, the machinery of multiple imputation can work, but you need different rules. And finally, there's a set of rules for nested multiple imputations. Nested multiple imputations are when you divide your missing values into two parts, y-1 and y-2. And you first generate y-1, and then for every value of y-1, you generate some values of y-2. So you have imputations of y-2 nested within y-1. And that sometimes helps if you really care about two different types of missingness and you want to see how much information is missing due to this part rather than this part. Now, one of the first questions that you get asked when you talk about multiple imputation is how many imputations do you need? How big should my M be? And if you look at the early references, you'll see that they say that only a few imputations are needed when the rate of missing information is not low or is not high. And there's this formula that the relative efficiency of the Q hat that you get is 1 over 1 plus lambda over m, where lambda is the rate of missing information. So that formula tells you that if you have, say, 30% missing information, you take 5 imputations, your estimate is highly efficient. Now that argument came out when computation was difficult and when imputations were expensive. With modern speed and storage, other considerations suggest that we should take more. And so these days, people routinely take 25 to 50 imputations, or sometimes even over 100. And I would suggest that you consider taking more than 100 if you need an accurate estimate of the rate of missing information. And my former student, Ofer Harrell, had some interesting, cute results about how many imputations you need to get an accurate estimate of that rate. And that rate is sometimes important for studies in non-response bias. Okay, now I'm going to talk about what is special about complex samples. When I say complex samples, I mean complex surveys, surveys with complex designs, and also censuses and administrative databases. What are some of the special issues and difficult problems that arise when you are in this context, often if you're working within a government agency? So the first issue I'm going to mention is possible incompatibility between the imputation model and analysis procedures. So for example, suppose you work in a government agency and you release a data set to the public, and the data set, the missing values have been multiply imputed, and they've been multiply imputed under a relatively simple model that assumes that some relationships among variables are zero. And then somebody takes that data set and looks for those relationships and finds out that those relationships look like they're not present. And that's an artifact of the imputation procedure. So if you're going to be releasing multiply imputed data for multiple uses and you don't know what those uses are, you have to think about this compatibility. And we know that it works if Rubin's definition of proper is satisfied, but that's difficult to verify in practice. And Xiaoli Meng's discussion of congeniality and super efficiency is also very helpful, but it's rather difficult to understand. I'll try to explain it in 1 minute. What are the important issues to take, or messages to take away? What I find working at a government agency is that we, the data producers who are also imputing, we often have access to extra information which is not released to the public and which will not be included in the analysis. Is it okay to use that information? Well, often yes, and often it's good to use it and it's helpful. And if you do this, this sometimes creates mismatch between the model used for imputation and the models that are being used for analysis. And that mismatch may either be helpful or harmful. And if the model that you're imputing under is more general, if it makes fewer assumptions than the analysis model, then you're okay. Then the analysis might not be as efficient as it could, but the results will be valid. Now, if you include extra information and make more assumptions than the data analyst, and if those extra assumptions are true, then you get a phenomenon known as super efficiency, which means that the answers that the analyst is getting is better than he or she thinks. The imputations carry extra information that the analyst doesn't know about, but that extra information is reliable. Now, the only danger arises is if you make extra assumptions and those assumptions are false. Then you can get mismatch. And that's, if you look in the, all the published examples where multiple imputation fails, that's what's happening. Another issue, popular multiple imputation software, and now I'm talking about software based on joint models. Many of them assume multivariate normality. So the very first program that I wrote for multiple imputation was assumed multivariate normality. And because that model is so easy to work with, and it is flexible to an extent, it's so computationally convenient, it's still being used widely. But survey variables tend to be categorical and mixed types. So in my 1997 book, I do have chapters on what to do if you have categorical data or mixed data. And I talk about log linear models and general location models. And they are useful when the number of variables is small, say no more than 20. But once you get more than 20, these models become very difficult to deal with because of the contingency table just gets too large. So in those settings, what people do various things. One technique that they do is they impute a categorical variable as if it were normally distributed, and then categorize the imputed values by rounding or coin flipping. And there are different methods for doing this, and sometimes they work well. There's been a few papers talking about when they fail. Something that I am becoming more a fan of now is models for mixed variables based on a latent normal structure. So if you have, say, a binary variable, you create a model where that binary variable is a categorization of a underlying normal variate, and that corresponds to a multivariate probit model. And these have nice computational properties, and this class of models falls under the umbrella of multivariate copula models, and there's a nice growing literature on that. Now, these have not been widely implemented, but I believe that's going to be the next generation of popular imputation models. Another issue that comes up in our world is potentially large numbers of variables to be imputed. So it's fairly easy to do a good job if you're just imputing, say, income. But if you have to impute 100 variables, that's tricky. Now, with a joint normal model, you can reduce the dimensionality of the covariance parameters. You can start imposing restrictions. You can assume an underlying factor structure. You can smooth towards some structured covariance matrix. And there's been some techniques published for doing that. These are very nice, but they're not widely available. The software still isn't there for doing that. Right now, if you have a potentially large number or a large number of variables, the only real game in town is a fully conditional specification or chained equations, so using IVE-ware or mice. Now that has a theoretical problem in that if you specify these regression models for each variable given the others, you may not actually have a set of regressions that's compatible with the joint distribution. That's been known for a very long time. In practice, this doesn't seem to matter much. I haven't really seen any real examples where this creates problems. You can also do what Donald Rubin did in 2003, where he used a set of incompatible chained equations only to complete a monotone pattern in the data, and then he imputed sequentially under a proper joint model. Now, we often have complicated interactions when we're dealing, especially with categorical data from surveys and censuses. And if you're working, say, with a normal model and you're rounding off normal variables to their nearest category, you have to remember that the normal model doesn't have any interactions. There are simple correlations between variables, but there's no three-way associations in the normal model. Now, you can preserve three-way associations, some of them by data splitting. If you know that you have two variables that you want to preserve their interaction with sex, you can split by males and females and impute separately, so you have different covariance structures for males and females, and that preserves the three-way association. So you can do some limited data splitting. You can also include interactions in sequential regression models. If you don't want to explicitly specify what those interactions are, you can do sequential regression with random forests. And there's some nice capabilities in mice for doing that. And there's also been some new work on non-parametric Bayes modeling based on some complicated Dirichlet process mixture models, where you don't actually have to specify what the interactions are in advance, but the Dirichlet model, the Dirichlet process model finds them. But still, that's still a very experimental technique. Now, if you are working with a survey that has a complex design, suppose you have stratification and clustering, that ought to be reflected in the imputation model. If you don't reflect that somehow, then you can have an imputation model that's not congenial with the analysis. Now, the usual advice that we give people is that you should include in your imputation model fixed effects for stratifying variables or stratum indicators and random effects for clusters, and which suggests you should be using multi-level multivariate models. And there are some models for doing this. You can also use these techniques to preserve cross-wave correlations in longitudinal surveys. Rod Little and his colleagues have been advocating, even if you do this, even if you take your stratifying variables and clustering into account, you can still include, say, some features of the sample weights in your imputation model to help guard against model failure. And there's some good evidence that this helps. Now, there are also some methods for including mixed effects models in sequential regression. So if you're using an IVE-ware or mice type approach, you can include random effects in those individual regression models to reflect the correlation, the clustering in your sample. Now, we also often have hierarchical or multi-level data structures. So for example, suppose you have an educational survey that's based in schools. So you might be sampling schools, and then within schools you might be subsampling teachers and collecting information on teachers nested within schools, and you can have additional levels of clustering. That's very common, and early procedures for multi-level imputation assumed that we had only missing values at the final level, at the smallest level of data collection. Now, there are some techniques for dealing with missing values at different levels. There is a set of chain multivariate models for different levels where you're treating the levels in your imputation procedure like you would treat variables in a chained equation procedure. Folks in the UK, Carpenter, Kenward, and Van Stieland, have a package called RealComImpute, which handles missing values at different levels. I still don't have any experience with that software. I'd be curious if any of you do. But that looks rather promising. And the book by Carpenter and Kenward that came out 4 years ago with applications in MLWin has some discussion of this. Now, this does not solve all of our problems. So, for example, in the talk we heard this morning about what folks are doing at Stat Canada, in the Stat Canada census, just like in the United States Census, we collect data at the household level, and so individuals are clustered within households, but there are very complicated sets of relationships and among individuals within the household. You have their relationships to the first person, relationships to the second person, relationships to one another. And those are very, very difficult to incorporate into any kind of imputation model. And that's largely an unsolved problem. And this is related to the fact that imputed values need to satisfy logical constraints. So if you are doing multiple imputation in a context where you also have to deal with logical constraints, you need to build those logical constraints into your model so that your model assigns zero probability to something that's illogical or inadmissible. And there has been some work on how to do that when you have, say, questionnaire skip patterns, where if somebody answers no to a question, then all the other questions after it in the section become irrelevant. You can also have to use, you can have sum constraints where you have variables that are known to sum, say parts of income have to sum to a total income. That can be tricky to handle if your sum constraints are on the income scale, but your model is modeling log income. It becomes a set of log linear constraints. Those are difficult. Now, another issue that arises is that explicit edit rules may imply other constraints, so-called implicit edits that must be satisfied. Finding these implicit edits requires very complicated set covering algorithms and integer programming. And my colleague Bill Winkler will be happy to tell you all about those and how hard they are, because they are difficult. And you also have the issue that even if your observed values pass edit tests, the observed values themselves might not be error-free. And you might need or want to consider multiple imputation to account for response errors as well as missing data. So in that setting, you would treat the knowledge of whether a value is correct or incorrect as a missing value, and that would be multiply imputed, so that in some of your data sets, that value would be removed and re-imputed, and in some data sets, it would be left alone. There's a lot of very interesting problems to work on in that area. And here is a problem that I deal with a lot now that I'm working on business surveys. Semi-continuous variables and unusual marginal distributions. So a semi-continuous variable is a variable that has part of the responses are zero, and then the non-zero responses are continuously distributed and usually highly skewed. So income is a great example, income of a certain type, or expenditures. How much money did you spend on shoes last month? You'll get many zeros, but then you'll get a skewed distribution. And if you try to model these variables, they can be very tricky. So here is an example of one of these variables where I have the zeros, a spike for the zeros, and then I have the positive values on a log scale. And I also have the dotted line is the fitted normal curve. So a log normal model really doesn't fit this data, and I'm finding this again and again, that the log normal that has too heavy of a tail on the right and not enough tail on the left to accurately model this kind of data. And if you use that log normal as an imputation model, it can lead to disaster, because you're getting a few imputed values that are unusually large on the log scale. When you exponentiate them, they become totally huge and influential and implausible. And so you have to model the tail on the right hand correctly, and also the tail on the left hand. You need to model it correctly. And so this suggests that we need to look at some non-parametric modeling techniques to get these marginal distributions correct. And finally, I'm going to finish with some talk about some non-statistical considerations. So one thing that I find is when you're sitting at a university writing papers and publishing and doing research, it's very easy to think that you've solved a problem because you've established something in theory. When you start to put it into practice in a real-life problem, all sorts of complications arise. And many of these complications are very serious, but they're non-statistical. Now, I just showed you a whole bunch of techniques, a whole bunch of references, a whole bunch of work that's been done on multiple imputation that has really advanced the science in the last 15 years. But many of these techniques still are not ready for prime time. They're still not ready for people at statistical agencies like the United States Census Bureau to just pull off the shelf and start to use. And some of those problems are statistical, and I talked about those, but there are many non-statistical issues, and a lot of them relate to the availability, reliability, and sustainability of software. So I think many of you probably know this. It's very difficult for a statistical agency to to create software for a specialized purpose and then keep it going over the long term. because maintaining that kind of software, keeping it updated, is really challenging when you're doing all sorts of other work as well. And many times the techniques that you want to use, you know that you could use them, but no one else has written the software and you don't have time or expertise to write the software yourself. So that's a huge barrier that needs to be overcome in many problems. There is the perceived and actual difficulty of implementing in a production environment. So it's one thing to do imputation on a toy problem. It's another entirely different matter to do multiple imputation in a situation where you have to produce results and publish them by a certain date. And implementing a complicated model-based imputation procedure in that tight production time schedule can be very challenging. Then there is also the perceived and actual difficulty of explaining to policymakers and to the public what you're doing. And you can tell them, oh, I imputed under a big multivariate model, and my model is really good because of this and this and this, and they won't know what you're talking about. And it's not, you could have the best model in the world, but depending on the environment that you're in, it still might not pass muster. And so you've got to be very careful about how you talk about it. Now, I have a very interesting story about that. I won't go into details, but I had some involvement with a project at the Census Bureau back in 1990. So that was almost 30 years ago when I was still a graduate student. And we were doing multiple imputation in a survey. We were doing multiple imputation. And one of the highest ranking officials at the Census Bureau said, well, your multiple imputation method looks really interesting, but why don't you try a hot deck? I want to see the results from a hot deck. And we went away and we thought about it. And we came back the next day and we said, well, the fact is, doing a hot deck is actually harder than doing the multiple imputation the way we did it. And then he said, okay. A hot deck is easy to explain to a non-expert, but in practice, it's pretty hard to implement. And some of these complicated model-based techniques involving Markov chain Monte Carlo are actually easier than hot decks, at least in my opinion. And then finally, there's a matter of organizational culture and priorities. Do we really have an organizational commitment to data quality that would press us to actually care about doing a really good job of handling non-response? And that's not a question that I can always answer, but I do know that to the extent that methodologists and statisticians make the extra effort to communicate well with other parts of the organization, it can only help. And I thank you for your time, and I'll just say that if you want to see references, they're in a separate document. I loaded it onto that computer. If you want to see the bibliography, just send me an email, and I'll be happy to email it to you. Thank you.
Muy bien, muchas gracias. Tenemos tiempo para algunas preguntas.
Thank you very much for your talk. Just want to ask, for the first step of imputing the missing data, in which context can we use the EM algorithm?
That's a great question. The EM algorithm is a technique for finding maximum likelihood estimates. And so EM is great for getting parameter estimates when you have missing data. If you want to do multiple imputation, you don't just fit the imputation model and get parameter estimates. You also have to get some accurate assessment of the uncertainty in those parameters. And the EM algorithm is not very good at that. But fortunately, the kinds of Markov chain Monte Carlo algorithms that we use to do the multiple imputation, in many cases, they're very closely related to EM. And if you can write code for EM for a problem, changing it to a Markov chain Monte Carlo to do proper multiple imputation is often very, very easy. So, but they're close, very, very closely related. And also, if you can implement an EM algorithm for the problem, looking at the behavior of the EM, especially how quickly it converges, that gives you some idea of how much missing information you have in your problem, and it's very informative. So I personally find the EM algorithm very, very helpful. You can't always do it. Sometimes the EM algorithm is too difficult. Sometimes Markov chain Monte Carlo is easier than EM, but sometimes they're very, very closely related.
¿Alguna otra pregunta?
Could you share experiences of you mentioned in this last slide on non-statistical problems or non-statistical issues, but can you share actual experiences that you have had in the Census Bureau?
I will say this. So for the first 18 years of my career after graduate school, I was in academia. Then I moved to the United States federal government, and the atmosphere, the climate or the environment was very different, because it's a very, working at a government agency in many respects is different from the university. But I happened to come at a time where the United States Census Bureau had a very, very strong, renewed strong commitment to statistical research and methodology. And we had an associate director of methodology at the time, who was Rod Little, who co-wrote the book on missing data and knows all about this. And he was a very, very strong supporter of multiple imputation. So I was very, very fortunate and blessed to come in to the federal government at a time when the door was already wide open. The one person who was very, I would say, most opposed to doing model-based multiple imputation, he retired and I moved into his office. So times have changed. I think what Steph Van Buren said is correct. About 2005, there was a big cultural shift. And now you don't have to fight so hard, at least among methodologists and scientists, to argue that multiple imputation works and that it's a good thing. There's still, the biggest hurdle is operationally. There are many people who are involved in production who will say, well, I understand that multiple imputation is good, I'd like to do it, but we just have no time to do it. And so you as a researcher have to be willing to then form long-term relationships with them and help them. And so that's basically what I'm doing now. And I have no complaints. I think it's, the atmosphere now is very, very open and very, very receptive to this kind of research. And I hope it lasts.
¿Más preguntas? Bien, pues agradezcamos al expositor.